We are here at Analytical Answers, a company which has been performing materials and failure analysis for more than 25 years. Over that time, they've completed over 50,000 analyses, a high percentage of which deal with surface chemistry and composition, which is what we'll discuss here today with Darlene Reed, one of the surface scientists here at Analytical Answers. Now, Darlene has a BS in chemistry from Carnegie Mellon University and an MS from the University of Oregon. She's analyzed hundreds of samples throughout her career and has taught laboratory courses on the practice and theory of ESCA analysis. She's also an avid volunteer for the Science Club for Girls, helping to nurture the next generation of scientists. So Darlene has a wealth of experience on ESCA, which is what she's going to be talking about today, and how it applies to the analysis of surface chemistry and composition. So with that, I'd like to hand it over to Darlene. Welcome, Darlene.
Good afternoon, everyone. As Christina said, my name is Darlene Reed. I'm a surface chemist here at Analytical Answers. And today we'll be talking about the surface chemistry of biomaterials, coatings, and electronic materials. And we'll be talking about these topics through the lens of analyzing them using ESCA and SAM. ESCA stands for electron spectroscopy for chemical analysis, and SAM stands for scanning Auger microanalysis. So here's a quick overview of what we'll be talking about today. First, I'll define what I mean by surface. We may all have different definitions, and so I'd like to clarify that. Then I'll talk about the instrumentation needed to analyze the surface, both ESCA and SAM. And then we'll talk about 6 examples. These examples are broad examples. AAI deals with proprietary samples, so I will talk about broad examples that can be applied to these 3 topics, and then at the end we'll have time for questions. If you have a burning question and I can see it in the chat, then I'll try to answer them. If not, then I will try to get to them at the end. This presentation is approximately 30 to 35 minutes long, so let's begin. So the surface of any sample is important, and I'm talking about the top few nanometers. ESCA and Auger analyze the top few nanometers. A standard technique that is used to analyze the surface of many materials is SEM-EDS, and SEM stands for scanning electron microscopy and electron dispersive spectroscopy, and that analyzes any sample on the top 1 to 3 microns, and so that's what this book represents, the full thickness of the information depth that comes with analyzing SEM-EDS. If you compare ESCA and Auger analysis to that, we're only analyzing that top cover, the top few nanometers, so that's at least 3 orders of magnitude difference between the information that you're getting from a SEM-EDS and the information that you're getting from ESCA and Auger. And this is important because the surface is inevitably different from the bulk. The surface is your material's first line of defense against the outside world, the environment, whether it be mechanical or thermal stress, dissimilar metals, gases, or vapors. Your surface will slightly change from the bulk of your material, whether it's a passivation layer or an oxide. And ESCA and SAM can help us to characterize that change and analyze it so you can better understand your material. So ESCA stands for electron spectroscopy for chemical analysis. It is also known as XPS, X-ray photoelectron spectroscopy. Whenever someone mentions XPS or ESCA, they're talking about the same technique. This technique uses an X-ray source to bombard your sample's surface, and we collect and measure the kinetic energy of core electrons being emitted from that sample. The benefit of using an X-ray source is that you can analyze both conductive and non-conductive samples. And on the screen here, I just have an example of an XPS. You can use both a monochromated aluminum source or non-monochromated source. And the difference there is just in an aluminum monochromated source, you're using one particular energy of the X-ray continuum to bombard your samples, where a non-monochromated source, you're bombarding your sample with the entire X-ray continuum. This technique is a practical application of Einstein's photoelectric effect. And that effect simply states that if you bombard a sample or an atom with a photon, you'll emit core electrons, and that core electron or photoelectron will have a very specific binding energy. That photoelectron will have a spectrum, and those binding energies will be the same every time no matter what energy you bombard the sample with. The second peak that we can analyze using ESCA is an Auger electron. So we have photoelectrons as well as Auger electrons. And an Auger electron is a result of a relaxation period when this atom is in the excited state from this emission of a photoelectron. An electron can fill that vacancy, and when it does, that transition releases energy, and that release of energy causes a secondary electron to be emitted. That is called an Auger electron, and we can see both in ESCA analysis. But as I've stated previously, Auger electron spectroscopy is its own technique. It's also known as scanning Auger microanalysis. Here, pictured on the left, I have an Auger nanoprobe, and the source of an Auger, as you'll probably hear me refer to it the rest of this presentation, is a field emission electron beam source. The benefit of having an electron beam source is you can get an SEM image of the area of analysis. The downside is you're only able to analyze conductive materials or semiconductive materials. And here we look at the kinetic energy, we measure the kinetic energy of these Auger electrons. Now this is an image of what's going on once your sample is bombarded with an electron beam. As I stated before, the book was kind of one example, but here you see that most of the data you're getting from SAM or EDS is coming from that 1 to 3 microns on your sample surface. A lot of your EDS information are coming from these characteristic X-rays, backscattered imaging from these electrons, and SEM imaging from these secondary electrons. These Auger electrons that I'll be speaking about are coming from that near surface region. So again, a 3 order of magnitude difference between SEM and Auger and ESCA analysis. So that was pretty fast, so I'll just go through really quickly the differences and the similarities between the two techniques. ESCA has an X-ray source, which allows us to look at both insulating and conductive samples. Because we're using X-rays as a source, we're able to look at a large area, hundreds of microns, but it also gives us the capability to understand chemical bonding of any material. So is carbon singly bonded to oxygen? Is it doubly bonded to oxygen? Is it bonded to fluorine? Slight shifts in the binding energy allow us to understand what's going on. So quick way to remember ESCA are X-rays in, electrons out. For SAM or Auger, AES, we have a field emission electron beam source. Because we have an electron beam as the source, we're able to look at small features on the order of tens of nanometers and also get an SEM image of the area that we're analyzing. We can look at conductive or semiconductive samples but not insulating samples. And so a quick way to remember Auger are high energy electrons in, low energy electrons out. They're similar because they both can analyze the sample, the chemistry of a sample, the top few nanometers. Neither can detect hydrogen or helium, and they have up to 0.1 atomic percent sensitivity, and they both can do depth profiles. Depth profiling is a way to understand your material as a function of depth. If you think about the book example I gave in the beginning, it's like analyzing the composition of the cover page, turning the page and analyzing the composition of the title page, so on and so forth. And so you can really understand your sample as a function of depth by sputtering through or removing material and analyzing what's underneath. So now I'll begin with our first ESCA example. Here I have a corroded copper penny. As you can see, they have some reddish regions here, a kind of blue whitish region over here, and a scratch area. This broad example can be applied to the world of electronic materials. If you think about a copper lead frame, copper wires, sometimes they get discolored or corroded and you would like to understand why, but this can be broadly, this can apply broadly to many materials. If you're thinking about surface contamination on the surface of a semiconductor die, thin films, glass, ESCA is a great technique to use to analyze surface contamination. So here are a close-up of those regions that we saw on the previous slide. This is what I'll be calling a reddish region or area. Here it would be the blue whitish region, and the circles represent the spot size of our ESCA. And here we have a scratch region. So this is surface contamination. We know something has reacted with copper. I scratched a region to see if I can get back to that metallic copper underneath to really see if it's truly a surface contamination. So here's the survey scan, and this is generally a wide range scan that we do with ESCA. Here on the x-axis you will see that we have a binding energy, and it's in descending order, and on the y-axis we have the counts of electrons. So ESCA measures the kinetic energy of the photoelectrons coming off of a sample, and so we switch the scale to read for binding energy, but if this were kinetic energy it would go from left to right in ascending order. Each element will have multiple photoelectron peaks, and so here we see that the reddish area of this copper penny has mainly carbon and oxygen. That makes sense. It's a corroded penny. Maybe it has some organics from laying about. It has copper and zinc. Also makes sense. Pennies made after 1982 or 85 are zinc and actually copper plated. And so the last thing we see here are sodium and chlorine. And that may begin to give us a little bit more information on why this copper penny began to corrode. Here we have high resolution spectra. The difference between a survey spectra or wide scan and high resolution spectra are the windows we take a look at. So instead of looking at 1100 binding energy, we are looking at 20 to 50 EV or electron volts. And on the y-axis still are the counts of electrons. So the important number here is for the 2p3 binding energy. They vary by 0.7 EV. And I'd like to stress that copper is a unique case. Generally, shifts in binding energy from metallic to oxide states can range anywhere from 0.5 to 3 plus EV. But copper needs both the photoelectron binding energy shifts as well as the Auger electrons to really detail what's going on in the sample. So we have both here. The scratched area where I was trying to get back to the metallic surface of that copper penny, we can see that the Auger supports that this is metallic copper, as well as a little bit of this copper 1 oxide. This sharp peak shape also provides support that this is the metallic area of the copper penny. So it is a surface contamination. I was able to get back down to that copper plating, but there's still a bit of that copper 1 oxide left. The red area has more of that copper 1, but it still has that copper carbonate, which is those bluish specks that we saw. I guess the most famous example of copper carbonate would be the Statue of Liberty and its bluish color. So we can suspect from there that this penny has been exposed to water vapor. In this blue-white area, there seem to be multiple oxidation states because these Auger peaks aren't as sharp as the other two we've seen. And so very clearly from this example, we've kind of identified what that copper is bonded with, and armed with this information, we'll be able to know how to remove it and what conditions it was in to cause it to be this way. So on to our second example. This ESCA application has to deal with coatings. Quite often, substrates go through a surface treatment to modify the surface energy and increase these adhesion capabilities. On metals, it would be a chemical etch or mechanical abrasion to the surface, and on plastics, it would be a plasma treatment. So before we looked at a metallic sample, now we're going to look at an insulating sample. Our next scenario is an example of a client walking in with four plastic samples, and they're trying to distinguish what's the difference between their adhesion properties. They have a good sample that adheres very well, a control sample that hasn't gone through any processing to provide a baseline, and two questionable samples that adhere but not as well as the good sample. And so ESCA is an ideal technique for this because with an X-ray source, we don't have to worry about the samples being non-conductive. So let's take a look at the spectra. The unprocessed material has 99% carbon and 0.9 to 1% oxygen, and we know this is a polystyrene. And so if we move on to the good sample, we see that it went through a plasma treatment and that was an oxygen plasma treatment with this 23.8% of oxygen and trace levels of fluorine. So if we take a look at our first questionable sample or questionable sample that does not adhere as well as the good sample, we see that it has a very similar composition to our unprocessed sample. So this did not go through the processing treatment at all. Excuse me. The second questionable sample seems to have gone through a fluorine treatment and not oxygen, since we have 63.8% fluorine and only 35% of that carbon present, only 1% of that oxygen present. And so very quickly we were able to tell that one sample did not go through the processing treatment at all, and that caused the less than ideal adhesion capabilities, and one went through a plasma treatment, but it was the wrong gas that was used. ESCA is also very useful in understanding the surfaces of functionalized groups as well, and so this example was an example of that. Our third example is the silverware of metallized plasticware. So on the surface this looks like silverware, but as you can see it was easily broken, and like us, had you observe it with your own hands and eyes, you would see that it was lightweight. And so this is the plasticware that you would see, the disposable plasticware you may see at birthday parties. And so the question to us was, okay, we know it's a coating on a plastic, but can we analyze that further? And so our survey scan shows that the surface of this spoon was iron and oxygen mainly. It has a little bit of carbon just from surface contamination being out at atmosphere, as well as chrome, molybdenum, and nitrogen. And so what I suspect is that this is a stainless steel that's been oxidized on top of a plastic, on top of the plastic substrate. So the question is this one coating? Are there many coatings? We can do a depth profile to understand what's going on. So this is a depth profile. On our x-axis we have time. So this is how the material is changing over time, where on the y-axis we have the concentration. And so if you were to take many of those survey scans and kind of stack them up over time as we remove material, you can kind of track the concentration of each element as we sputter away at material. And so as we see here, we see a high concentration of iron and oxygen on the surface. That oxygen quickly decreases to a baseline, and we see alternating peaks of iron and titanium oxide. And so what this suggests to us is that there's a thin film metal stack, and that thin film metal stack is alternating between the stainless steel and the titanium oxide. The chrome is high on the surface and then goes to a baseline, and we see baseline levels of that nickel and molybdenum, which support the stainless steel theory. Here we have the titanium oxide. It's probably the adhesion layer that's allowing the plastic to adhere to the rest of the metal stack. And so that is a depth profile, and we can actually combine this technique, ESCA, with FIB, focused ion beam, and get an image of what's going on. So here is a cross-section of a metallized knife, and we see that there are alternating about 6 layers, similar to what we saw in this slide, of the stainless steel and the titanium oxide. Here is the adhesion layer, which is a little larger than those thin films, and this pure black region represents the plastic, or that pure organic. This is useful when you're analyzing your thin film metal stack, simply because you want to make sure that it is the right thickness as well as the right composition. But this is also useful for optical coatings, where the thickness of your thin film is directly related to the wavelength that is reflected back at you. And so ESCA can be combined with FIB to get you the analysis that you need. So our last ESCA application is actually combined, can also be done on OJ, and it is another depth profile, but of a passivated stainless steel. So passivation of metals becomes crucially important when you're talking about biomaterials. And although I have stainless steel here as an example, passivation becomes important for surgical tools that are made of stainless steel, but are also important when you're talking about stents. The oxides that grow on the surface, the near surface region, help in the corrosion resistance and help with biocompatibility. And so here, characterizing the oxides that grow on the surface of metals becomes crucially important. So here we have that oxygen and chromium are the major elements on the surface of this stainless steel sample. And that's important because what makes stainless steel stainless or rust-free is that chromium content. Stainless steel has 12 to 17% chromium, and that percentage of chromium preferentially binds to oxygen and creates that passivated layer on the surface. So we see that that oxygen content decreases pretty quickly after about a minute of sputtering, and that iron content increases, that nickel increases and gets to a baseline, and that chrome, while it's abundant on the surface, kind of decreases to a baseline level in the bulk of the material. And so after 1 minute represents the bulk of the stainless steel, and before then represents that oxide layer. Well-passivated stainless steel or metals normally have a passivation layer on the order of about 10 nanometers, and that is enough for corrosion resistance. Now, where oxides may be beneficial in the world of biomaterials, keeping corrosive elements out and harmful elements from leaching out of the material or metal itself, it can be harmful in the world of electronic materials where you're trying to, let's say, electroplate a surface. And so understanding or characterizing the passivation on your metal in order to remove it may be beneficial in the world of electronic materials, where understanding and quantifying the thickness of a passivated material in the world of biomaterials becomes important for the quality of your material. Our first SAM application, or scanning Auger microanalysis, also known as Auger electron spectroscopy, has to do with thin films. And what's suspected is the diffusion of the substrate into the above layer. Now here, SAM can also be combined with FIB. Here we have a cross-section turned on its side, where the substrate is on the left-hand side and the surface is on the right. And we're trying to analyze if the composition of each layer. So here the substrate is copper and the film on top is tin, and we kind of see 4 layers here. This probably is a substrate, an intermetallic in the middle, but the question is, what's the composition of this layer? Is it pure tin, or has the substrate diffused into the layer above? If you were to do this analysis using SEM, because of the information depth, you would probably blast through and get straight down to the substrate. So what we'll do is take this cross-section and do a line scan. The line scan reveals that indeed that leftmost side or region was copper. We do see an intermetallic where there's both copper and tin, but where we suspect the top layer should be purely tin, we still see that copper is present. And we know we've reached the surface because we see an increase in the platinum. That is a protective layer when you're doing a FIB cross-section. And so we do see that although they vary in terms of contrast, copper has diffused to the surface to the thin film on the surface. And this is important when you're talking about failed wire bonds or thin metal stacks or solderability. You want to make sure that your metal stack has the properties you need it to have and that no metals are diffusing into the above layer. Our last and final example has to do with the evaluating physical appearance or characteristics, and this can apply to coatings or electronic materials. And the example I have is the aluminum housing you've received from a supplier differs in physical characteristics. Some are shiny, some are dull, and you're wondering, one, is there a difference? Is one better for what I'm trying to do? Now the supplier has assured you that they both have the same capabilities for what you need them to do, but you want to be sure, so you take a look at the surface chemistry. With Auger, we take a wide range scan, and here we report the kinetic energy on the x-axis, and again the raw counts of electrons on the y-axis. And we see when we look at the percentages that the ratio of aluminum to oxygen is quite the same. And there's a small amount of carbon contamination, but not a large difference. And so the shiny side, the dull side, on the surface there's nothing that would differ one from the other. So we take a look, maybe the oxide thicknesses are different, causing one to be more shiny or dull than the other. So we did a depth profile over about 3 minutes, and we looked at the concentration of aluminum and oxygen and tried to really pinpoint when that oxygen goes away and we get to that aluminum substrate. In about 2 minutes we get to that aluminum substrate, and that happens on both the dull side and the shiny side. So the question is, what is the difference? With SEM, because we do have that SEM image to go along with our surface analysis, we see very quickly that the shiny side is flatter than the dull side that has a rougher texture. And this is important to remember when you're evaluating physical characteristics, that although you may suspect a chemistry change on the surface, it could also be morphological. And to keep both in mind, or when both are in question, Auger is the ideal technique to use. So here's just a quick review of all that we talked about today. Our first example was the surface contamination and understanding the chemistry of any discoloration you may find on your surface, and ESCA is the ideal technique to do that. You can understand chemical bonding as well as everything that may be on the surface. The second thing we talked about were surface coatings and treatments as it applies to adhesion. And there you can use ESCA because it's to analyze insulating materials, as well as if you wanted to analyze if you functionalize the surface of your material, ESCA is an ideal technique to use. Next thing we talked about was thin film composition and using depth profiling to understand your metal stack and that it has a proper composition and that you maybe have no contamination, as well as the thickness, which is useful for optical coatings. Understanding both composition and the thickness of a thin film stack is very useful in that field. And ESCA and FIB can be used to analyze that. For biomaterials, we talked about characterizing the passivation oxides to ensure the corrosion-resistant nature and the biocompatibility of those materials, and how depth profiling, either with ESCA or Auger, is possible. And we also talked about understanding and characterizing those same oxide thicknesses on metals and how it can be useful in the world of electronic materials when you're trying to electroplate and remove those oxides. Knowing how much is there so that you can apply the proper techniques to remove it is very important. The second to last thing we talked about was about diffusion of a substrate into a thin film, and understanding that it's crucially important to use SAM to understand what's going on there, simply because it may affect your solderability, as well as maybe apply to why your wire bonds are failing, just as examples. And then the last thing we talked about was how surface chemistry and surface morphology are important things to consider when you're talking about physical characteristics. And when both are in question, that SAM or Auger is the ideal technique to use. So, thank you for your time. Again, my name is Darlene Reed. Are there any questions?
So it's 12:31, and we are going to be here for another 15 minutes. So if you have any questions right now, please feel free to ask any questions. You can type them into the chat, or you can type them under questions, but you can type them. We're not going to unmute anybody because it can create a little bit of reverb. So if you do have a question, on the right-hand side of your screen, there is a chat box, and we will answer them as they come through. We would like to remind you in the meantime again about the upcoming webinars, and we've got a couple of them coming up. One is going to be October 18th, and the other one is going to be in November. And we'd like to remind you that it's at analyticalanswersinc.com/fall webinars. And we are going to be sending out a reminder for everybody who was on this webinar to register for the next one. You'll also be automatically registered, so all you're going to need to do is click on the link right when the webinar is going to happen, and you will not have to go through the registration process again. We want to remind you that the October 18th webinar is about polymer analysis of biomaterials, composites, encapsulants, and adhesives, and November 15 we'll be talking about thin film and multi-layer defect analysis in metals, metal coatings, and optical coatings. This webinar, again, it's going to be recorded, so if you missed anything or if you come up with a question afterwards, you can re-watch the webinar as well as asking any questions on by emailing us at answers@analyticalanswersinc.com, and we'll be happy to follow up with you. So we'll just stay here and wait for any questions for about another 8 minutes. We also want to remind you that we have coming up in December a couple of pre-recorded demos that we're going to be sharing with you, so that even though it's the holiday season and it's a busy time for us all, you will be able to continue the learning at your own pace and your own speed. We also have a growing library of pre-recorded webinars that we'll send you a link to as well. So again, as the holiday season approaches, I know not all of us have time to take time from our busy day and sit at our computers and watch a live webinar, but you can watch pre-recorded ones. And again, if you have any questions as a follow-up, you can ask them. Again, either in the chat right now or send us an email at answers@analyticalanswersinc.com. So with that, we do want to stick around because we did promise that we're going to be here to take any questions, and also remind you that we have a blog. So we have day-to-day questions, features, and topics that could be of interest to you. Some of them are fun scans related to food. Some of them are fun scans related to everyday objects in our environment, but we definitely want you to take a look at the blog and ask any questions in response to those. So we have a quick question here coming in from Nick. Are they suitable for powders? Darlene, are any of these techniques suitable for powders?
So ESCA can be used to analyze powders. We do have a special holder for them, but as long as it doesn't outgas, then we can definitely analyze powders using ESCA analysis.
For hydrogen analysis. Just the hydrogen analysis question. What do you recommend for hydrogen analysis?
So for hydrogen analysis, that requires a different technique. I can get back to you through an email with the particular analysis needed for that, but if you wanted to analyze organics, FTIR is an ideal technique for that. But for hydrogen analysis, the acronym is escaping me at the current moment, but I can reply by email at what the ideal technique for that is.
What technique is better for bond pad cleanliness?
For bond pad cleanliness, the ideal technique, because of its size, would be Auger analysis. If you're concerned about any processes that, or evaluating how well you're cleaning your samples, Auger is the ideal technique.
I actually got asked twice.
So depending on the size of your semiconductor die, ESCA or Auger would be ideal to analyze the surface contamination or the cleanliness of that sample. So we have a question here. It says the carbon content in the, I believe it's from Russ, the carbon content in the metallized silverware is mainly due to stainless steel, not atmospheric exposure, correct? So actually that may be from atmospheric exposure. As you, I'm sorry, one second, let me go back to that slide. But if we go back to that slide, maybe a while ago. No, it was a while ago. Okay, here we go. So because that carbon decreases very quickly, it was only about 14%, and that generally represents anywhere from 1 to 3 nanometers on the surface of a sample. If it were a part of the stainless steel, then you would see the carbon most likely follow the trend of the iron throughout the stainless steel. So I would say that the carbon is from surface contamination, and then as we see at the end it increases dramatically, so it's related to the plastic. Okay, we have another question. Were the dark spots identified in the copper tin line scan example seem like voids are possible? They were not. We were just looking at a broad area analysis. Sorry for the fast clicking through. But no, the voids were not analyzed specifically. We probably looked at areas that represented a majority of what those areas looked like. Oh, you're talking about here in the intermetallic region. No, they were not analyzed exclusively. Okay, we have another question. Detection of polymer residue on metal wire after laser ablation, submicron thickness. Does it belong here or in your next polymer webinar? It could actually be both. So sometimes ESCA and FTIR are used to analyze this type of polymer residue. With submicron thicknesses, ESCA may be ideal to understand what's going on there, but FTIR may give a better distinction of as to what type of organic residue is on the surface.
Okay, so we've worked through all of the questions that have come in. So again, using either the chat or the questions, please share any other questions that you do have. But again, there's a little bit of overlap between the different topics. So if you didn't see exactly what you're looking for in this webinar, either ask a question or certainly tune into the next polymer webinar, because we're going to be going through a variety of topics in that one as well. So feel free to continue to ask away. Okay, we have another question coming in.
All right, this question states, can you depth profile down to a buried interface in an optical coating to look for contamination, and which technique is ideal for that scenario? We can depth profile down to an interface. The most important part of that question would be how thick is the optical coating and what type of contamination you're looking for. But ESCA would be used depending on the size of your optical coating for that technique. Both ESCA and it could be combined with FIB to make sure that we're getting through the proper thicknesses and the thicknesses are what you believe they are. But ESCA would be used to depth profile and then FIB to kind of confirm that we've gotten down to the right layer. So we have another question, but I would need a bit more detail before I can tell you the ideal technique. This question states, we have pores located in the cross-section of our material. Would this be a good technique to analyze the composition? They're about a half a micron in size. I would need to know what type of material this was, but something about a half a micron in size is probably SEM EDS, depending on what that material is. Or OJ, but again, I'd have to know a little bit more about the material.
Okay, so it looks like we are pretty much out of questions. Again, we do need some further information on that last question, but if you want to follow up with an email, that might be better, and we could give you a bit more detailed answer, right? Thank you so much, Darlene. This was a really very informative webinar. Again, we are going to be sending out a recording of this, so if you missed anything, if you want to review it, if you want to share it with a colleague, that's going to come out. If you are registered for this webinar, you're going to get an email with that recording. So we are now closed for questions. If you want to go to analyticalanswersinc.com/fall webinars, join us on October 18th for polymer analysis of biomaterials composites with Jay Powell. And with that, I want to thank Darlene Reed again for her really wonderful sharing of information on ESCA today. And we hope to see you at our next webinar. And again, if you have a follow-up question, please feel free to email us. And thank you for attending the first of our fall series of demonstrations and webinars. Take care.